Yesterday we stopped at coordination number 6. Let us continue with the coordination number 7. Better strength even in the rain. So let us begin with coordination number 7. Can you give me any geometry for coordination number 7? Trigonal? Bipyramidal? No. Trigonal bipyramidal is coordination number 5. Yeah, pentagonal bipyramidal. Distorted? Octahedra. How many faces? 5 faces above, 5 faces below, 10 triangular faces. For 7 we can also have monocapped octahedra. This is simple octahedra. Anywhere you can put a cap. This is monocapped octahedra. Octahedra has how many faces? Octahedra, 8 faces. But one face is getting capped. One face is getting embedded. So don't count this face. But new cap is providing how many faces? 3 faces. New cap is providing 3 faces. I am just showing it. This is one face of a new cap, second face of a new cap, third face of a new cap. So for any triangular face, if it is capping, you remember 3 new caps will arise. If a triangular face is getting capped, 3 more new faces will come. If a square face gets capped, 4 faces will come. So here octahedra, 8 faces of parent, 1 is getting embedded, 7 from parent, 3 are new. Altogether 10 triangular faces. Can I call it as a deltahedra? Can I call it as deltahedra? Yes, because all are triangular faces. These are deltahedra. For the same 7 we can also have monocapped trigonal prism. This is trigonal prism. So whenever we put a cap, you try to put it to a square face only, not a triangular face. Put a cap for a square face towards your left or towards your right or away. So suppose if I am taking towards your left, 1, 2, 3, 4. Trigonal prism has how many faces? 1, 2, 2 triangular faces, 3 square faces. But 1 square face got embedded. So we have 2 square faces. Up and down 2 triangular faces. And the new 4. So 6. 2 square faces, because 1 square face has got embedded. Along with that 4 triangular faces are coming. So altogether 6 triangular faces and 2 square faces. I am just showing you trigonal prism. Okay, first you watch it and then one triangular face towards you, one triangular face away from you, or else I can hold it like this. Okay, one triangular face above, one triangular face below, one square face towards your left, one square face towards your right, one square face away from you. So 2 triangular faces and 3 square faces. Any of these square face will get capped. So one square face got capped. Okay, either you put it towards your left or right or away, it is just one and the same. If I put it towards right, this is how it looks. Or if I am keeping it away, what is the point group of this? Anyone? If it was simple trigonal prism, it belongs to D3H. Simple trigonal prism belongs to D3H. What is the point group of this? I cannot rotate by 120 degree. Those who are aware of symmetry, once you get through the elements, you will be easily understanding. But those who already know symmetry, I cannot pass a C3 because this was towards bottom side. Now it is moving towards your right hand side. C3 is not present. But from here, can I pass a C2? C2 is possible. Okay, can I pass a plane? Can I pass another plane? Yes. So monocapped trigonal prism belongs to C2V point group. Okay, monocapped trigonal prism belongs to C2V. These questions will also come in the exam. In one of the reaction mechanisms, we have Ray-Dutt twist racemization, Bella twist racemization and Ray-Dutt twist racemization. In that we will be having some intermediate. That intermediate will be this trigonal prism, and they will ask you what is the symmetry of that intermediate. That was a previous exam question. So you should be aware of all these things. Okay, question may come from any part. If you want, you can just write it. It belongs to C2V. Then let us move to coordination number 8. Bicapped octahedra. Where will you put the 2 caps? Either you can put side by side or you can put opposite. If you put side by side, we call it as cis bicapped. If you put opposite, we call it as trans bicapped. So let it be cis or trans. How many triangular faces? Parent has 8, 2 are getting embedded. So 6 from the parent, 3 and 3. Altogether 12 triangular faces. Monocapped has 10. Bicapped has 12. Bicapped trigonal prism. If anyone can tell me the point group. Okay, before going to point group, above there is one triangular face, below there is one triangular face, 2 triangular faces from the parent, 4 plus 4 newly added. So 8 plus 2, 10 triangular faces This square face and this square face got capped, so away there is one square face. Whichever face is embedded, don't include it. 10 triangular faces and one square face. I'll try to show the molecular model. You tell me what point group does it belong to. Just for a while you watch it and then you can draw. This was monocapped. Okay, this belongs to C2B. Later on I am putting one more cap. This is the structure. What point group? Though there are two triangular faces eclipsed to one another, I cannot pass a C3 because these two, there is no third one. Only two are capped. So I cannot pass a C3 because if I pass a C3, it looks unsymmetric. No C3 possible. But can I pass a C2 from here? C2 is possible. Can I pass a sigma V? Another sigma V. So bicapped trigonal prism belongs to C2V. Monocapped C2V. Bicapped C2V. Simple trigonal prism D3H. Simple trigonal prism D3H. Trigonal prism D3H. Monocapped C2V. Bicapped also C2V. Another important geometry is square antiprism. For square antiprism, first of all you put two squares staggered to one another. Now you just watch again. In the trigonal antiprism I said top to bottom, bottom to top, towards you and away from you. The same thing you follow. 1, 2, 3, 4, 5, 6, 7 and 8. So altogether how many faces? I drew 8 lines. It means 8 triangular faces in between. One square face above, one square face below. So there are 8 triangular plus 2 square faces. 8 triangular plus 2 square faces. Point group is D4D. Square antiprism is D4D. I told you a logic. Whenever you have two identical symmetrically substituted units eclipsed to one another, that molecule belongs to D and H. If they are staggered, D and D. So here I am having two squares which are identical symmetrically substituted. They are staggered. Therefore D and D. How much is N? For square means it is 4. C4. So it belongs to D4D. What is other name for square antiprism? Other name for square antiprism? You call it as Archimedean antiprism. Archimedean antiprism. This is also square antiprism but in a different view. Same thing. In some books it is given like this, in some books it is given like this. Both are one and the same, you need not get confused. Next one is hexahedra or cube. Six square faces. Point group is OH. Next one, octa-decahedra. First you draw this. 6 are completed. 7th and 8th. 7th and 8th. For this, so if you are able to look it carefully, everyone, just a minute. You just look at these two, this one and this one. How many vertices or how many edges are coming? 4. For this, 4. Now look at this one. 4. For this one also 4. So these two are 4, these two are 4, they are like staggered. Okay. Next look at this one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So these two and these two will be staggered. These two will be staggered. For these 4, it will be 4 vertices, sorry, 4 edges. And for these 4 it will be 5 edges. So accordingly you try to draw. It will be having 16 triangular faces. The name itself says octa-decahedra. Octa-dec. Sorry, 18. Not 16, 18. Octa-decahedra. 18 triangular faces. Can anyone tell me the point group of it? I gave you a hint. Okay. Just try to imagine, later you can draw. The top 2 will be like this. The top 2 vertices will be like this. Okay. Next 2 will be like this. On board we cannot draw like this. Okay. First 2, second 2, third 2, fourth 2. Got it? 2, 2, 2 and 2. Each of them will be staggered to one another. What could be its point group? See? D4D. Little change. It is D and D because whenever you have such units, consider the first and the last. How is the first 2? Like this. Next 2. Next 2. Next 2. So first one is in this direction, second one is in this direction. How are they? Staggered. Are they like staggered or not? Just like Allin, 2 CH2 units are staggered. So this belong to D2D point group. Okay. Note down. Octa-decahedra belong to D to D. Next, coordination number 9. Tricapped octahedra, how many faces? Parent has 8, 3 are embedded, 5 from the parent, 9 are coming from the caps, so 9 plus 5, 14 triangular faces. Tricapped octahedra, 14 triangular faces. Next one, you take tricapped trigonal prism. I am showing you, later I will draw. This is tricapped trigonal prism. What could be its point group? And how many faces? There were 1 and 2 triangular faces, 3 square faces, but every square face got embedded. So don't count those square faces because they got embedded. Each square face is giving you 4 triangular faces. 4, 4 and 4. So 12 new triangular faces, 13 and 14. Altogether 14 triangular faces. So suppose if I am taking a tricapped trigonal prism or I am taking a tricapped octahedra, how many faces are there? 14. And what are they? Triangular. Whether I take this geometry or that geometry, you have 14 triangular faces only. Same thing. Tricapped trigonal prism or tricapped octahedra, same. Okay. But one important point that you have to remember is, for octahedra, I said 3 faces. So where should you imagine these 3 faces? Are you able to imagine an octahedra? I'll just show you shortly, but are you able to imagine an octahedra? Suppose if these are the 2 triangular faces, other 2 triangular faces, 4 triangular faces above and 4 triangular faces below. Altogether 8 triangular faces. 2 towards your right and left, 2 faces towards you and away from you below. Above, 2 faces towards you and away from you, 2 faces towards your right and left. Altogether 8 triangular faces. Okay. Whenever I say monocapped, try to put that cap towards your right hand side triangular face above, as per convenience. 1 triangular face. Second one towards your left hand side, cis. If it is stands opposite, let me take cis. 1 and 2 towards your right, towards your left. When it comes to third, don't put third here. Below it will come towards you. Third will be towards you. Fourth will be away from you. Okay. So 1, 2, but below when it comes not 3 and 4. 1 and 2, 3 and 4. That is how you have to imagine. Okay. Can you draw? Tricapped octahedra is done. Can you draw tricapped trigonal prism? Meanwhile, I'll just show you the model for octahedra. Whatever we see, we remember for a longer time. So for symmetry and clusters, I just take some extra time to show the models. Done with it? I'll just show octahedra. Later on we'll be drawing it. This is a simple octahedral model. One triangular face towards your left, towards your right, towards you, away from you, above. Below also, away from you, towards your left and towards your right. Let me put a cap. Suppose if I am starting to put a cap towards your right hand side. Okay, this belongs to CS point group. Monocap octahedra belong to CS. Bicapped could be trans or cis. Let me start with a cis. This is cis bicapped. Okay, if I take the tricapped, I should not put it here below. I have to put it towards you or away. This is the third cap, and fourth cap will come away from you. Away means I'll put it and then I'll show. This is tetracapped octahedra. Okay, the same structure I'll hold it in a different way. How is it looking like? Pyramid. It is just looking like a pyramid, but this pyramid is holding an octahedra inside. It is holding an octahedra inside and it is tetracapped. But if I look it in a different way, it looks like a pyramid. Okay, so this is tetracapped octahedra. In this case, if you are able to imagine, suppose if I am passing a plane, this plane is taking up how many atoms? 1. Second plane is taking up 1, 2, 3 atoms. Third plane is taking up 6 atoms. 1, 2, 3, 4, 5, 6. So every time a plane, triangular plane is being constructed. This is a small triangle, larger triangle. If I go for the next one, how many atoms could be there? How many? I'll give you a hint. Let me show you like this. If I'm holding it like this, for this smaller triangle, 1, next row 2. Larger triangle 1, 2, 3. If I take still larger triangle, 1, 2, 3, 4. 1 plus 2 plus 3. Next larger triangle will be 1 plus 2 plus 3 plus 4. It will be 10. Are you able to imagine? That will be the structure of the cluster osmium 20, CO40 cluster. We have a cluster osmium 20, CO40. This is the structure of osmium 10 cluster. And if I remove this larger triangle, smaller triangle is the structure of osmium 4 cluster. So it is just like a triangular unit slowly constructing. Okay, are you able to imagine now? First only one vertex, second a small triangle, third larger, fourth still larger. That we call it as cluster growth. Cluster, not crystal growth, cluster growth. We'll discuss in organometallic chemistry. Meanwhile, you start drawing, don't wait for me. You can draw coordination number 9, coordination number 10. 10 is tetracapped octahedra. It will take time for me to construct these structures, but once you watch all these things, it will become easy for me in the next classes. let me show you trigonal bipyramidal. Remember the model carefully. Trigonal bipyramidal. This is pentagonal bipyramidal. Can you see a qualitative difference between these two? What is the qualitative difference? Qualitative difference is, for trigonal bipyramidal we say axial bonds are longer, equatorial bonds are shorter. Can you experience in this? These are longer, these are shorter. So this looks like elongated way, but this one, it looks like compressed. So there is a qualitative difference. This is TBP. This is PBP, pentagonal bipyramidal, trigonal bipyramidal. I am giving you like a polyhedral structure. But when I go to transition metal complexes or coordination complexes, we imagine a metal inside. These are considered to be ligands. Or if I consider it as a cluster, all of these are like metals, polyhedra. Okay. Now are you able to imagine octahedra? Monocapped, bicapped, tricapped, tetracapped octahedra, trigonal prism, monocapped, bicapped and tricapped, PBP, TBP. Okay. I am trying to show maximum number of geometries. When we go to higher level, we cannot show all of them. Tricapped octahedra. Have you drawn tricapped trigonal prism? One cap towards your left, one cap towards your right, one cap away. I am just showing it in a dotted way because it is like away from you. How many faces altogether? 1 and 2 triangular faces are still intact. 3 square faces have been capped. Each square face is giving you 4 triangular faces. 4 into 3 plus 2. So it is 12 plus 2, 14. This is tricapped trigonal prism. Fourth one is away from you, therefore I am putting a dotted kind of a structure. It is like away. This is towards you, this is towards your left, this is towards your right. Altogether how many triangular faces? Parent has 8, 4 are embedded, so 4 are coming from parent. Each embedded face is giving you 3 more triangular faces. New faces are 12. Old faces, I mean the parent faces, 4. So altogether 16. Is it easy to remember? Octahedra, how many triangular faces? 8. Monocapped. Monocapped. 8 minus 1, 7 plus 3, 10. 8, 10. Bicapped. Tricapped. Tetracapped. So is the pattern easy? 8, 10, 12, 14, 16. Starting from octahedra to tetracapped octahedra, you just increase 2 triangular faces. This is coordination number 10. For coordination number 9, do you have any other geometry? Coordination number 9. I think trigonal prism tricapped is completed. We have one more geometry, I will show you. This was square antiprism. If I am putting a cap above, this is coordination number 9, monocapped square antiprism. For coordination number 9, you also add this. Monocapped square antiprism. How many triangular faces were in between? 8. New one is adding 4. 12 triangular faces. 2 square faces were there, one was embedded. So remaining 1 square face. For coordination number 9, we also have monocapped square antiprism. For 10, I can take bicapped square antiprism. One cap I am putting below. And 1 cap above. For this, how many triangular faces? 8 are in between, 4 above, 4 below. Altogether 16 triangular faces. No square faces, both square faces got embedded. Can you tell me the point group of monocapped square antiprism? Anyone? Simple square antiprism D4D. Simple square antiprism belongs to D4D. Monocapped square antiprism belong to C4V. C4V. One square face got capped. Still I can pass C4, but C2 is perpendicular to C4 will be gone. So monocapped square antiprism belong to C4V. Bicapped square antiprism, again D4D. Just as its parent, it will retain D4D. Square antiprism D4D. Monocapped square antiprism C4V. Bicapped square antiprism again D4D. Coordination number 11. Dot game. We are playing dot games. Are you able to see all these dots? First draw 2 pentagons staggered to one another. 2 pentagons staggered. This one I will keep it above. Below you just join them. Finished up till this point. This vertex joined to this pentagon. Completed up till this. Later above and below should be joined. Just look once and then you can draw, everyone. Starting from here, top to bottom and bottom to top will continue. 2, 3, 4, 5, 6, 7, 8, 9 and 10. So in between how many triangular faces you got? 10 triangular faces I got. Below already there were 3. Above there are 5. So altogether there are 18 triangular faces. It is little bit difficult to visualize this, but it belongs to C2B point group. Octa-decahedra. The last one with coordination number 12. Any geometry? For coordination number 12. Put 2 pentagons. Staggered. Then one vertex above and one vertex below. So how many triangular faces I got? Above 5, below 5, in between we will be getting 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This belongs to IH point group. It has the highest number of symmetry elements, 120. The number of symmetry elements present in them are 120. Can you give me any example for icosahedral structure from our inorganic chemistry? We have B12H12 2 minus borane, or you can also have a carborane C2B10H12. C2B10H12. It will have what you call super aromaticity. Not simple aromaticity, it will be having super aromaticity, super aromatic. "26 electrons, does it obey Huckel's rule?" 26 electrons. Does it obey Huckel's rule? 4n plus 2 pi electron. 4, 6, 24 plus 2, 26. So if I take n equal to 6, it will be Huckel's rule. Okay. If at all it obeys 4n plus 2 pi electrons, 26 electrons, it is called as aromatic in your organic chemistry. In the organometallic chemistry, if I have 26 skeletal electrons, I can call it as super aromatic. Super aromatic. C2B10H12 is super aromatic. Okay. Note down an example for icosahedra. Take an example. Example is C2B10H12. C2B10H12. C2B10H12, write a point. With 26 skeletal electrons, it is referred as super aromatic structure. It is referred as super aromatic structure. Super aromatic structure. please make a correction. Before diagram, for coordination number 8, I gave a structure octa-decahedra. One octa-decahedra I gave with D to D point group. Please correct it. It is not octa-decahedra. It is, write down, triangulated dodecahedra, not octa-decahedra, dodecahedra. Make a correction. Dodecahedra. This is octa-decahedra. This one. This is triangulated dodecahedra. Please make a correction. Not octadecahedra. It will have 12 triangular faces, not 18. This octadecahedra overlapped with this structure. So just make a correction of it. Why should we say triangulated dodecahedra? Because we also have pentagonal dodecahedra. Pentagonal dodecahedra is also there. It is a platonic solid. This is triangulated dodecahedra. All faces are triangles. It is a deltahedra. That one correction. Okay. So we are completed with all the different types of geometry, starting from coordination number 2 up till coordination number 12. When we go to clusters, we also have coordination number 13, 14, 15, 16. But it is very, very difficult to draw them. We can also have coordination number of 13, 14, 15 and 16. 13, if I just show, it will be like a triangle, hexagon and a triangle, one more atom in between or in the center of that hexagon. That will be like coordination number 13. If I go to coordination number 14, structures are very, very difficult. So patterns will be difficult. So we are not going for that. Okay. In clusters, I will show the cluster structure of 13. Number of metals equal to 13 I can show. Just a small hint of it. The structure will be something like this. So if you are able to watch it clearly, this is a triangle towards you above, then is a square face, then is a triangle towards your right hand side, again a square away, triangle towards your left hand side and a square face. So square, triangle, square, triangle, square, triangle above. Below also same, but it is like staggered. If this is triangular face, below will be square, square, triangle, square, triangle, square, triangle, and the 13th atom will be in center. This is for coordination number 13. We simply call it as hexagonal cubic closed pack structure. This is shown coordinated with the hexagonal atoms. So how to draw it? First of all, I have taken a triangle. Below there is another triangle. These two triangles are staggered, if you have noticed. In between there is a hexagon. Above and below triangles are staggered. Later you connect in such a way that triangle and square face, they are alternating. Can you tell me how many faces are there? How many faces in it? 8. Okay, above how many triangular faces? Triangle, square, triangle, square, triangle, square. 3 triangles, 3 squares above. 3 triangles, 3 squares below. 1 triangle on the top, 1 triangle at the bottom. So altogether 8 triangular faces, 6 square faces. Okay, note down. 8 triangular and 6 square faces. 8 triangular and 6 square faces. This structure is not explained even by Weights. Weights rules or PSEPT, polyhedral skeletal electron pair theory, failed for these structures. So they went for another kind of a theory called as hexagonal cubic closed packing structures. Finished? Okay. Now just for few minutes you listen, then we'll go to the main points of symmetry. In the last class I told what exactly means symmetry. Symmetry is measurement of repeatedness or measurement of similarness of some patterns present in a given entity. When I say entity, the entity could be a simple atom or an orbital or a wave function of that particular molecule. If I choose a molecule, maybe I have chosen butadiene. Butadiene will have one particular symmetry, let it be cis or trans. Trans will have one and cis will have another point group. And even for that cis butadiene, you will be having 4 wave functions, psi1, psi2, psi3 and psi4. So I can even consider the symmetry for those wave functions. Or I may take allene. Allene will have one point group. Okay, and maybe if I consider allene, it will be like C2V point group. But again for that allene I have psi1, psi2 and psi3. For each of these wave function, again I have to consider the symmetry. So I can take any chemical entity, and for any chemical entity I can consider the symmetry. I have to just work out all the symmetry elements and operations provided. I have to collect all the symmetry elements together to make it a point group. And once I know its point group, I can know about some characters of that molecule. How many spectral peaks does it give? How many translations or how many rotations are present in it? How many vibrations are there, of which how many are IR active, how many are Raman active, whether it is optically active or inactive, whether it is polar or non-polar. All these characters I can deduce just with the help of symmetry. Okay. Right. Before entering into symmetry, just a few guidelines are needed. I'll give you some molecule. I'll ask you to perform symmetry. Directly will you perform on it, or do you need any guidelines? We definitely need some guidelines. Suppose I'll ask you to work out the symmetry of a water molecule. Okay. Then what I'll do, water molecule, hydrogen, oxygen, hydrogen, I'll put it in a line, linear. Then I'll work out. Whatever point group that I get, it will be wrong. Because what is the structure of water? It is angular. Okay, it is angular. So when I say it is angular, the symmetry elements will be different. So the first thing that we should know is the geometry of a molecule. Without knowing the geometry of a molecule, I cannot work out symmetry elements and operations. Okay, so this we call it as a prerequisite, the minimum requirements to work out a point group. First thing, I should know the structure of a molecule. Second thing, once I know the structure of a molecule, you should identify where is the center of gravity for that molecule. Where is the center of gravity for oxygen or hydrogens of water? Where is the center of gravity in water molecule? Does it exist in oxygen or hydrogens? Oxygen. And if I identify the center of gravity, any symmetry element has to pass through the center of gravity only. I cannot pass it from anywhere else. For any molecule that I choose, I have to identify the center of gravity, and through that center of gravity, every symmetry element has to pass. Let it be a plane, or let it be a point, or let it be an axis. They have to pass through the center of gravity. But every time we don't say center of gravity, we say center of the molecule. Every time center of the molecule is not center of gravity. Remember, there are some asymmetric molecules. For that asymmetric molecules, center is not the center of gravity. I have to identify the center of gravity, but for what do you call writing purposes or discussion purposes, we always say center of the molecule. Okay, center is not the center, but it is the center of gravity. Okay, two things. First one, minimum structure or geometry of the molecule has to be known. Second one, I have to identify the center of gravity. Third one, proper orientation of molecule is also important. Proper orientation means I am imagining water molecule like this and then I am passing it. Or one of the students, what he will say, I'll imagine it like this. No problem, you can imagine. But as a beginner, if you are imagining water molecule to exist like this, you may miss some symmetry elements as a beginner. Okay, once you are aware of all the symmetry elements, however you may orient the water molecule, you are able to pass the symmetry elements. But in the beginning, you should know the proper orientation of the molecule. These three things are the minimum requirements. Geometry or structure of the molecule, identifying the center of gravity of the molecule, and orientation or proper holding or proper imagining the molecule. These three are prerequisites. Right? So any molecule, you have to imagine that it is present in the Cartesian coordinates or the Cartesian space. This Cartesian space is defined by three coordinates. We say x, y and z. I'll just show the three coordinates, you just follow me. This is one coordinate, this is second, and this is third. Three coordinates. By convention, I give this as z. That is by convention. You may take it as x, you may take it as y. But for symmetry purposes, generally we take this as z, x, y. Okay. So if I am pointing like this, you imagine it is a axis. This is z, this is x, this is y. Y is towards your right and left. Plus y minus y, right and left. Z plus z minus z, above and below. X plus x minus x, towards you and away from you, or front and back. Okay, we have three coordinates which defines this space. Suppose if I am present here, from this particular space, where can I move? I can move only in three directions. One is towards my right and left, one is towards you and away from you, one is above and below. Apart from these three directions, can I move in any other direction? Not possible. You may say, I can move diagonally. But even if I am moving diagonally, I am moving front and right. I am moving front and left. It is the combination of these directions. But altogether we have only three directions. That is why we say this is a three-dimensional space. Okay, in this three-dimensional space, I have only 3 degrees of freedom. Front and back, right and left, up and down. Okay, so I take any two coordinates, it will form a plane. Take any two coordinates, it will form a plane. Imagine this is z-axis, x-axis, y-axis. I am taking this x and z. What plane does it make? While drawing the d orbitals, we have drawn all the d orbitals in the beginning. So what plane is this? XZ plane. This is a XZ plane. What plane is this? YZ plane. XY plane. Okay. XZ. X. Y. Whether I show it like this or whether I show it like this, it is the same plane. So don't get confused. Whether I show a plane like this or whether I show a plane like this is XZ only. Are you getting it? I am passing it like this. You have to imagine and you have to remember all these things. This will continue for your group theory also. In group theory also they will give you one character table. In that character table you have to imagine a water molecule undergoing a translation along x, y and z direction means water molecule is moving like this. What is its symmetry? Water molecule is moving in this direction. What is its symmetry? Water molecule is moving in this direction. What is its symmetry? Everything you have to imagine. Okay? Right. So again I am showing. What is this plane? XZ. This is also XZ. YZ. YZ. XY. XY. Roof and floor. Roof and floor. XY plane. Right and left walls. Side walls. Your side walls. XZ. Front and back walls. YZ. So board is always in your YZ plane. Opposite to the board is also YZ plane. So front and back YZ. Your sides XZ. Roof and floor XY planes. Okay. If you are able to imagine, that will be easier for you. Z, X, Y. And any two coordinates that I change, any two coordinates that I mingle, it will become a plane. Understood? So just write down. Prerequisites for passing symmetry elements. Prerequisites for passing symmetry elements. First one, geometry. Write a point. A decent knowledge of geometry or the structure of a molecule. A decent knowledge of geometry or the structure of a molecule must be known. Or must be present. I said a decent knowledge. Yeah, must be present. Okay, just look at the examples. I have given you CO2 and N3. First or second, which structure is correct for CO2? First one or second one? First one. For N3, first or second? First one. I did not just give the charges, but is it the correct structure? Because N3 is azide ion, it will come as N3 minus. So this is minus, this is plus, this is minus. Here also I can indicate this is minus, this is plus, this is minus. But is this structure correct or is this correct? Is this right or is this right? For symmetry I can consider the second structures also. What is the reason? In symmetry I am not counting the number of bonds. I am nowhere related to VSEPR. I am nowhere related to chemical bonding. As far as the structure is like linear, let it be a single bond, let it be a double, triple, quadruple, quintuple or sextuple, does it change its symmetry? It will not change. CO2 belongs to D infinity H. Whether I put two double bonds or if I put two single bonds also, it will be D infinite H only. But if at all there are single bonds, if you bend it, it is a problem. Don't bend it, because I said the first point is you should have a decent knowledge of the geometry or structure of the molecule. Once you know the geometry, whether you put triple, double or a single bond, the geometry doesn't change. Understood? In some of the CSR exams, they can directly give you N single bond N. They'll give you some molecule, metal. That metal is attached to dinitrogen. Between those two nitrogens, there will be a triple bond, generally. But instead of the triple bond, directly they can give you a single bond. Don't say that he is wrong or she is wrong. It need not be. As far as symmetry is maintained, you can either show single, double or triple. Geometry should not distort. Okay? Geometry should not get distorted. If it is not distorted, any bonds you can keep. No problem, up to symmetry only. If you put bond changes in chemical bonding, it is wrong. But for symmetry, it is accepted. Okay? You can just take. So while giving point group, suddenly if I don't put a bond, don't say, sir, don't know about chemical bonding. It is not about knowing about the chemical bonding. It is to maintain that particular structure or not. So any of those two structures can be considered for symmetry. Next point, center of gravity. Center of gravity. For any given chemical entity, write a point about it. For any given chemical entity, ENTITY, for any given chemical entity, center of gravity must be identified. For any given chemical entity, comma, center of gravity must be identified. identified. Continue. Any symmetry element has to pass through the center of gravity only. Every symmetry element has to pass through center of gravity only. Next, broadly center of gravity is referred as center of the molecule. Broadly, center of the gravity is referred as center of the molecule. But in reality, every time the center of gravity need not be the center of the molecule, but just for our conversation I can use the term center of the molecule. Okay, don't get confused in future. What is implication? I have drawn water molecule. I am passing the rotational axis from the oxygen because I identified oxygen as the center of gravity. I am passing from the center of oxygen again. In the oxygen, where is the center of gravity? Again it is in the center of oxygen. So don't try to show the line. Suppose if this is oxygen, don't try to show it like this. It has to again pass through the center only. Okay? Can I pass it through the bond between oxygen and hydrogen? No. That is not the center of gravity. If I try to pass, I will say C2 is absent, but C2 is present in it. These are basics. As a beginner, everyone should be knowing it, because when we go to point groups, all these basics you have to just construct. I'll give you a molecule, you have to directly tell me the point group. You have to pass all the symmetry elements, you have to tell me the point group. Okay? So you have to do lot of workout. Completed? Note down the third point. Proper orientation or imagination of the molecule. Proper orientation or imagination of the molecule. Within the Cartesian space. Within the Cartesian space is also required. Within the Cartesian space is also required. Within the Cartesian space is also required. I am showing a rotational axis like this. Can I pass it? The right and the left half, are they looking symmetric? No, they are not looking symmetric. Then immediately if I orient the molecule like this and if I pass it like this, I may say it is absent. But actually it is present. So how you are holding or how you are imagining the molecule, accordingly you have to pass the symmetry element. But for a beginner, suppose if I draw the structure in a different way, suddenly you may say that particular axis is absent. But it need not be. You have to imagine in a proper way. So that is the reason we say try to imagine or try to orient the molecule in the Cartesian coordinate properly. Then you can imagine all the symmetry elements. Okay? That is what we call it as orientation of molecule. Very often when I give you substituted benzenes, some students, not many, some, they get confused. Suppose if I give you this orientation, what is the point group of this? Do you have C2? Anyone? Is C2 present? Can I pass a C2? The same thing, if I give it like this, both are same. In this case you have to imagine that the C2 is passing between these two. It could be difficult for you to imagine, but the same thing if I orient like this, It becomes very easy for me to imagine. So this is what we call proper orientation or imagination of the molecule. If I am able to orient it properly, I can easily imagine it. Got the point? Okay, these are just a few guidelines. And finally, how many of you have seen these symmetry elements called as axis, plane and a point? How many of you have seen means? Are you seeing me? Am I present here? Am I able to see every one of you? You are present here. Have you seen a rotational axis? Anywhere did you see that axis moving here and there? No. Have you seen a plane moving here and there? So every symmetry element is purely imaginary. Very important point. Every symmetry element or every symmetry operation is purely imaginary. I have to imagine that an axis is passing through the oxygen of water molecule. Later I am performing rotations. So every symmetry element is purely imaginary. When I say cut the molecule into halves, literally I cannot take a molecule and cut it into half. It is not possible, but I have to imagine it. I have to just imagine. So we say a point, every symmetry element is imaginary. Okay, note down that point. All symmetry elements are purely imaginary. All symmetry elements are purely imaginary. So they are not real. I think most of you are from organic chemistry background. How many of you are from non-organic, inorganic, physical, analytical? You can raise your hands. 1, 2, 3, 4, 5, 6. Okay, good number. But most of you are organic background. What is this molecule? This is butene, butadiene. Which one? Allene. 3 options gone. Last option. Somebody said cumulene. This is not allene. This is not butadiene. This is not butene. This is cumulene. 1, 2, 3 double bonds. One after the other. Consecutive double bonds. 2 consecutive double bonds. Allene. 3 consecutive double bonds. Cumene. I'll just remove one so that you'll get allene. Everyone is aware of allene? Okay. This is allene. Is this allene? In the previous case, if you are able to remember, or just if you are able to recollect, 2 CH2 units, they were parallel to one another. For cumulene, 2 CH2 units were parallel. But for this, how are the 2 CH2 units? This is one CH2 unit, this is another CH2 unit. They are like perpendicular. We call it as like staggered. For symmetry point of view, I am calling it as staggered unit. For cumulene, you got a eclipsed type. You got eclipsed type. Okay. In this, if you are able to watch it clearly, if this is in this plane, CH2 is in this plane. Where is this double bond? YZ plane. XY, YZ, XY, YZ. This will alternate. Okay. Suppose if it is cumulene, double bond. Where will be the double bond? This was YZ, XY. Double bond will come like this. Not this. Double bond will come like this. And CH2 will come like this. So this CH2 will be parallel, and double bond and your what do you call CH2 units will be perpendicular to one another. Understood? Can anyone tell me what are the symmetry elements present in it? We did not study symmetry. We did not even start with symmetry elements. But just in the introductory class, if anyone can tell me the symmetry elements of allene. I told you this question was asked in CSIR only for just one option. I mean, what is the point group of allene? That's it. No other addition. What is the point group of allene? It was asked in part C. 4 marks just by writing D2D. Completed. D2D. I've told you the point group. If anyone can tell me the symmetry elements. Okay. Can I pass a C2 from here, pointing from these 3 carbons and pointing towards you? And if I rotate by 180, is it giving you equivalent configuration? What is equivalent identical will start in the next class. But this is just like an introductory class. Allene is a very important molecule. So from here, if I am passing a C2 and if I rotate by 180, it is giving an equivalent configuration. And if I rotate by another 180, it will give you identical configuration. We say C2 is present. For people who are able to find it difficulty, I am holding it like this. This is a C2. Previously it was pointing towards you along the x-axis. The same I can hold it along Z. Can I rotate by 180? Okay. So I am able to rotate it by 180. So there is a C2 passing from 3 carbons. This is the rotational axis. I have to imagine it. One C2 axis. Any other rotational axis in this? Any other rotational axis? In prerequisites I said orientation of the molecule or proper imagination of the molecule is very important. The value of that point you will come to know with the help of this allene. No other rotational axis, right? Suppose if I pass a C2 from here, from the central carbon, how are these 2 hydrogens oriented with respect to you? They are vertical with respect to you. I am passing a C2. How are these 2 hydrogens oriented? They are like horizontal with respect to you. I am saying with respect to you. Okay. Remember this point. I am not saying these are vertical. I am saying these are vertical with respect to you, seated. These are horizontal with respect to you, seated. Okay. So can I pass this C2? No. Can I pass this C2? No. Is it there? No. So how many C2s are there in the molecule? Where is it passing from? All the 3 carbons. There are 3 C2s. Not 1, there are 3. Where are the other 2? Now how to orient the molecule or how to imagine the molecule is very important. I'll show you. Instead of holding it like this, okay, I'm trying to show directly to camera so that even if you go home and watch it, directly you can see that molecule. I'm holding it like X. Okay, are you able to see it like an X? This one and this one. Is it looking like an X? Everyone? Is it looking like an X? In this X, you just try to take one reference point, any reference point. Let this be this hydrogen, this or this. Maybe for convenience, you may choose these 2 hydrogens which are towards you. If I choose this hydrogen which is towards your top and left hand side, this is top and left hand side towards you. If I perform any rotational operation, if this hydrogen is exchanged by another identical hydrogen, I say that rotational axis is present. Okay, let me see. Again I am passing a C2 from here. Previously I was holding the molecule like this. I passed a C2, I said it is absent. Now I am holding the molecule like this. I am trying to pass that same C2. And if I rotate, if this hydrogen is exchanged by another identical hydrogen, I say C2 is present. Is it present? Yes. Previously it was not there, but now I have oriented the molecule in a different way. Okay. So is this present now? Yes. I am passing another C2 from here. Is it present? Yes. Take a reference of this, or you take any reference. Is that exchanged by another identical hydrogen? Yes. So holding or imagining the molecule in a proper orientation is also very, very important. If I don't hold it like this, I cannot imagine those elements. But once if I know all the symmetry basics, then even if I am holding it like this, I can imagine I can pass a C2 like this. I can pass another C2 like this, diagonally. But as a beginner, imagining this diagonal C2s is difficult. So properly orient the molecule and then try to imagine. That will be easier for me. Got the point? Okay. Write the next point. To understand the symmetry of any molecule, there are three primary symmetry elements. There are three primary symmetry elements. Three primary symmetry elements. These are note down these three: axis, plane and a point. Axis, plane and a point. Do you use smart mobiles? Smart mobiles everyone is having? Anyone not having? I think everyone has. How many apps are there in your mobile? How many? Maybe I never counted what apps are there in my mobile. By default there will be some apps. I install some more apps. Altogether how many apps are there in your mobile? Exactly, can anyone tell me the figure? No one. Maybe one or two. There will be like OCD candidates. OCD means you are aware of, right? They will be counting each and everything. What is there, all details. So they will know how many apps are there in their mobile. But in general nobody knows. I don't count how many apps are there. You have a symmetry app. What is that app? Axis, plane, point. Just remember, app means axis, plane, point. Okay, by taking that symmetry element I can perform some operations. In the introductory class I told you, if I am a surgeon, if I am given with scissors, what will I do? I will be cutting it. If I am given with a needle, I will sew. Likewise, if I am given with an axis, I can perform rotation. If I am given with a plane, I can perform reflection. If I am given with a point, I can perform inversion. So those are called as symmetry operations. These are symmetry elements. They are symmetry operations corresponding to the elements. Okay. So altogether how many symmetry elements are there? How many? Basic symmetry elements are only three. One is axis, one is plane, one is point. If I consider two of these symmetry elements, I consider an axis and a perpendicular plane that forms an improper or an alternating axis of symmetry Sn. That is considered as fourth symmetry element, because it is a combination of already existing two symmetry elements, but the basic ones are three. The fourth symmetry element is Sn, or alternating axis of symmetry, where rotation is alternated by perpendicular reflection. 4. What is the fifth symmetry element? Altogether how many means? We say generally 5, but I am saying only 3 basic. Fourth one is a combination of the two. Fifth one is identity. That is a basic element. Basic element means, what is my name? Dr. Shashikant. I am in Hyderabad. Suppose tomorrow I go to New Delhi. What will be my name? It will be still Shashikant only. Okay, tomorrow I will go to, day after tomorrow I am in US. The other day I am in UK. So by changing the places, am I losing my identity? My identity is always there. I am talking to you. I am Shashikant. Tonight I'll be sleeping. What will be my name? I'll be still Shashikant, right? So I don't lose my identity. Every person has their own identity. Likewise, every molecule, whether you operate or don't operate, if you just leave it, it will have its own identity. That element is called as identity element. So whether you operate or don't operate, it will have its own identity. That is a fifth symmetry element. But basically how many means? 3. Axis, plane, point. Got it? So with this introduction, from the next class we'll move to the symmetry elements. Now whomever I ask, they have to answer from this side. I'll show either the axis, I'll show either the plane. You have to say immediately without any confusion from this side. Not xz, xy. Okay, I'm showing like this. Again, xy. I'm pointing means it is an axis. I'm showing my palm means imagine it is a plane. X. So this should be always in your imagination. X, Y, Z. Xz, Yz, Xy. If you are able to imagine, suppose when we move to group theory or within the symmetry also, I'll ask you in the octahedral point group or some other point group, or maybe I'll choose C2V point group. In C2V point group, dx square minus y square has which symmetry? Or in C3V point group, dx square minus y square or dz square has which symmetry? Then immediately what you have to do, you have to imagine like plus before you, dx square minus y square, because this is xy plane. This is dx square minus y square, dxy, dxz, dyz, dz square. So all these things should be in your imagination, and immediately you have to pass, okay, C2 is present or not. Sigma v, is it present or absent? Sigma h, is it present or absent? All these things you have to imagine. Okay? Now everyone close your eyes. Everyone, just for a minute. I will not do any black magic. You just close your eyes. You need not bother. Now just listen what I say. Okay, carefully listen what I say. You are in biogenesis, in 3rd floor. It is raining a lot. So immediately after the class, some of you are going to have some hot jalebi or hot mirchi or something else. You had a hot mirchi and samosa. This Sunday we have given a holiday. So some of you went for a Hindi movie, some of you went for Telugu, Tamil, whatever language that you are in. The other day some holiday we have got. So you went to Goa. You enjoyed a lot in the beach. From there you went to New Delhi. There was a beautiful sight of Taj Mahal. From there you watched Qutub Minar. And again you came back to biogenesis, listening to my symmetry class. Now you can open your eyes. Okay. 3rd person. Which one did you enjoy a lot? Which one? He enjoyed samosa a lot. Okay. Which of these you enjoyed? Taj Mahal. All. Taj Mahal. Okay. Samosa. Jalebi. Taj Mahal. Taj Mahal. All. She enjoyed all. So she even enjoyed my class. Because all means my class will also come. Now here is where our mind tricks us, or our brain tricks us. Okay? Why did I say proper imagination is more important? What did I say in the beginning? I said close your eyes and then listen to what I say. I just asked you to listen. But what did you do? You have imagined it, you have lived it. Some of you have lived eating samosa, some of you went, you have seen Taj Mahal also. This is the power of your imagination. Because from the next class we are going to begin symmetry. The same imagination I want in your molecules also. When I just asked you to listen, you have imagined, you have lived. The same thing you have to do for symmetry. When I ask you benzene, try to pass a C6. Benzene should be before you. Maybe you are holding that benzene like this, or maybe you are holding that benzene like this, it is up to you. But you have to imagine that benzene. Now before you there are 6 carbons symmetrically arranged. And suppose if I am holding that benzene like this, how are the p orbitals oriented? For each carbon, p, 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 p and p. These are the p orbitals. And these p orbitals are just like dancing. Dancing means first these two combine, they open, these two combine, open, these two combine, they open. That is your pi delocalization. They are alternating. These two combine, they open, these two combine, they open, these two combine, and it is like delocalization. You have to imagine those things. And if I say psi1 of benzene, then immediately instead of holding it like this, try to hold it like this. This is your benzene. Now there are 6 p orbitals, plus, 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 all plus above, all minus below. Now can I pass a plane like this? For that same benzene I am holding it like this. I am considering only the psi1, only psi1, not regular benzene, psi1 of benzene. In psi1 of benzene, above is all plus, below is all minus of p orbitals. Okay. Now I am asking you to pass this plane, xy plane. Holding benzene in xy, try to pass xy plane for psi1 of benzene. Is it present or absent? It is absent. Because above is all plus, below is all minus. If I am passing a plane, what is the role of plane? It will be reflecting the two halves. Above will be reflected below, below will be reflected above. So plus and minus will be reflecting into one another. It is not an equivalent configuration. So I cannot pass this plane. Okay. If it is a simple benzene, then I can pass this plane. But for psi1, I cannot pass. So all these things you have to imagine. Okay. How did you imagine your samosa and jalebi? Taj Mahal. Yeah, many people said Taj Mahal. This is like benzene. Whether you may imagine it like this, then p orbitals will be like this, 6. Or if you are able to imagine it like this, then these are the p orbitals. So for this p orbitals, if all this is plus, okay, imagine this is like plus, red. This fluorescent green is like minus. If I pass a plane, what will happen? All this red will reflect below, or else I am holding it like this. Minus is towards you, plus is towards me or away from you. When I pass this plane, this will reflect towards you. So are they equivalent? No. Previously it was minus towards you, now it is plus towards you. Both are not equivalent. So I cannot pass this plane for psi1 of benzene. Okay. Likewise, any wave function is given to you, any ion is given to you, molecule, whatever is given to you, you should be able to answer it. Right? Okay. So from tomorrow we'll begin with the symmetry elements. And please go through the basics.